I'm Kirsty Duncan. I'll be presenting our work, Relative Robustness of Quantized Neural Networks Against Adversarial Attacks. This is a joint work with my two PhD advisors, Katja Kamendenskia, Robert Stewart, as well as Michael Loans. All four of us are from the Lab for AI Verification at Heriot-Watt University. Neural networks are increasingly being moved to edge computing devices and smart sensors in order to reduce latency and save on bandwidth. With the ever-increasing size of neural networks comes the issue of how to fit these large networks onto resource-constrained devices, for example, FPGAs, mobile phones, and special-purpose robotics hardware. A solution to this is to use neural network compression in order to reduce the size of networks and fit them on smaller devices. There are two main methods of neural network compression. The first of these is weight reduction, where we remove redundant parameters from a network. This reduces the number of parameters in the network overall, reducing the size of the network. This also results in an increase in the speed of the network. The second main method is neural network quantization. This is where the precision of parameters in the network is reduced. The TensorFlow Lite framework, which we use in this work, reduces all parameters in a network from 32-bit floating point down to 8-bit precision. Neural network quantization is able to greatly reduce the memory requirements of a neural network with very little loss in accuracy. In the most extreme case, the parameters of a network are saved as binary values. We see here a graph from a work which does exactly that. In red, we have a full precision network, and in blue and green, we have two binarized networks. Along the x-axis are the training epochs. As we can see, it takes slightly longer to train the binarized neural networks, but the end result is that the binarized neural networks only have a slightly higher error than the full precision network, despite being much smaller. Neural networks are susceptible to adversarial attack, which is where an input which would be correctly classified by a neural network has been maliciously altered in some way in order to cause the network to misclassify it. We have an example here. On the left-hand side, this input has been taken directly from the MNIST dataset and is correctly classified by our neural network as a 4. On the right-hand side, the same input has been maliciously altered in order to cause our network to misclassify it as a 6. We refer to these maliciously altered inputs as adversarial perturbations of the original input. We sometimes refer to them as adversarial counterexamples while verifying our network, which we will get to later. In this work, we want to know how quantized neural networks respond to adversarial attack. We've seen many examples in the literature of approaches which aim to verify a full precision neural network. These approaches are able to either certify that a neural network is robust to adversarial attack within certain parameters, or to provide an adversarial counterexample, i.e., a perturbed input which successfully caused the network to misclassify, proving that it is not robust. There also exist verification approaches for binarized and quantized neural networks. And outside of the verification literature, we have some comparisons of quantized and binarized networks. We've seen from these that quantized and binarized networks will misclassify fewer adversarial attacks than full precision networks when presented with the same attacks. The scenario we are interested in is where a full precision network is first verified. If this network is certified as robust, we then want to check the quantized network. If our quantized network is also robust to the same inputs, we can say that the quantized neural network is robust relative to the full precision network. The other scenario is where the quantized neural network is fooled by some counterexample which did not fool the full precision network. If our full precision network is not robust, i.e. some counterexample has been found which our network misclassifies, We then want to check this also against the quantized network. Either our quantized network will correctly classify this counterexample, or the quantized network will be fooled into misclassifying by the same counterexample which fooled our full precision network. In this case, we say that there is a transfer of adversarial attack from the full precision network to the quantized network. This brings us to our two key results. The first of which, we found that quantized neural networks are 98.6 to 99.7% of the time robust relative to the same full precision network. We also found that adversarial transfer can be as low as 52.05% when the attacks on the network are subtle, and we will get to this notion of subtlety later on. So, the first thing we need to do is verify our neural network. We do this using the Deep Learning Verifier tool. This is a tool which is able to verify that for some input in a dataset and for some radius around this input, our neural network is robust. It does this by taking some radius from our original image and drawing an n-dimensional sphere in the input space around the input. It generates a complete and covering set of perturbations within this radius. If all of these perturbations are correctly classified by our neural network, we say that the neural network has been certified as robust. If one or more such perturbations is misclassified by the network, however, this perturbation counts as our adversarial counterexample and proves that the network is not robust. We can modify our search parameters, and by doing so, we can change the likelihood of our network being certified as robust. For example, by doubling the search radius from a Manhattan distance of 10 from the original image to a Manhattan distance of 20, we found that on average there was 2.6 times as many perturbations generated by the tool. This translates to a 1.4 times as likely chance of finding an adversarial counterexample. The next step is to compare our verified full precision network with our quantized network. This results in 4 different cases. In the first case, our full precision network correctly classifies all perturbations, and so does our quantized network. We call this relative robustness. In the second case, our full precision network correctly classifies all perturbations, i.e. it is robust. However, our quantized network is fooled by one or more adversarial counterexamples. In the third case, our full precision network is fooled by one or more adversarial counterexamples into misclassifying. However, the quantized neural network is not. In the final case, both the full precision and quantized neural network misclassify the same adversarial counterexamples. We call this adversarial transfer. In order to quantify the relative robustness and adversarial transfer of some quantized neural network, we evaluate it on every input in some data set in order to obtain percentage values for each of these two measures. We start by splitting the dataset into inputs which were correctly or incorrectly classified by our full precision neural network. The inputs which were incorrectly classified are discarded. For those which were correctly classified, we split further into 2 subsections: those for which our neural network was certified as robust, and those for which a counterexample was found. Next, we evaluate the same inputs with our quantized neural network and are able to obtain a number of inputs for which our network is relatively robust and a number for which we have our adversarial transfer. The relative robustness of a quantized neural network is simply the number of inputs for which we have relative robustness divided by the number of inputs for which the full precision network was robust. We evaluated the relative robustness of neural networks on two different datasets and for various subtleties of our perturbations, which is a concept we will get to later. We found that there was very little variation in the relative robustness of quantized neural networks when varying the datasets or varying subtleties, and that the relative robustness of our quantized networks was in general close to 100%. So what do we mean by the subtlety of perturbations? We saw before how increasing the search radius increases the number of perturbations generated and also increases the likelihood of finding an adversarial counterexample. This is because the perturbations generated by the tool for a larger radius are allowed to stray further from the original input image. As an example, here we have two adversarial counterexamples generated from inputs in the MNIST dataset. On the left-hand side, a figure 1 has been altered in order to get a misclassification for my network as 9. The amount of noise added to this image cannot exceed a Manhattan distance of 10 from the original input. On the right-hand side, when our radius is 4 times as much, the amount of noise added to the image in order to generate a misclassification can be far greater. We see here results for the transfer of adversarial attack from a full precision to quantized network for different values of the subtlety. As we can see, as our perturbations become more subtle, the adversarial transfer decreases to as low as 52.05%. We believe that quantization is able to remove some of the adversarial noise and stop the quantized network from misclassifying. In summary, it's widely been shown that the accuracy of a neural network can be well preserved after quantization. We have shown that the verified robustness of a neural network can also be well preserved after quantization. And on top of this, that there is poor transfer of adversarial attacks from full precision to quantized networks, in particular when these attacks are subtle. In this way, one can say that quantized networks are actually more resilient to adversarial attack than full precision networks. If you want to check out our paper, there's more in there. During this talk, we focused on the search radius when verifying our network. In the paper, we go into more detail on how we modify the intensity with which individual pixels can be perturbed. We also evaluate the robustness of individual labels from a dataset. So inputs from different classes are attacked, and we see how some classes are far more susceptible to adversarial attack than others. For example, we found that between two characters in the MNIST dataset, there was a 64% difference in how often these classes were fooled. Most of the examples in this talk focused on the MNIST dataset, however, we explore two datasets in the paper. You'll also find a link to our GitHub with all the accompanying code. Last of all, thank you very much for listening. If you want to check out the paper, the title is Relative Robustness of Quantized Neural Networks Against Adversarial Attacks. I'm Kirsty Duncan, and the other authors are Katja Komendetskia, Robert Stewart, and Michael Loans. We are all a part of the live research group at Heriot-Watt University. I very much look forward to answering any questions. Thank you.